going on, everybody? Just wanted to show you some pictures of the moon that I took this week. The first one here was taken on March 30th. You can see that nice crescent moon. We call this a waxing crescent because it's just past new moon. Now, as the moon orbits the Earth, it goes through these phases. So the next picture here is a picture of the moon taken on April 1st. So 2 days after the previous one. And you can see it's no longer that crescent. It's just past half lit up. We call that a waxing gibbous moon. So I'm taking pictures of the moon every couple of days here. I want to show you how the moon goes through its phases. Now the moon goes through its phases because it orbits the Earth. And the moon actually orbits the Earth in an ellipse. Kepler's first law says all planets orbit the sun in an ellipse. Well, it's just not the planets. Moons do that also. Our moon is actually, it can be as close as about 235,000 miles away from the Earth and as far as 250,000 miles away. Sometimes you hear that term supermoon, and all a supermoon refers to is when the moon is at what we call perigee, its closest approach to the Earth, at that 235,000 mile mark. Sometimes the moon could be really far away when it's full, at 250,000. So just like the planets in our solar system, the moon also orbits the Earth in an ellipse. So I'll show you some more pictures as time goes on, and we can see the moon go through its phases. Part of your work this week was to work with the PhET animations with the University of Colorado. The first one here shows a perfect circle. Now, none of the planets orbit in a perfect circle, but we measure the shape of an orbit or the ellipse. We call that eccentricity. So when you have an eccentricity of 0, your ellipse is a perfect circle. Now, as that number gets closer to 1, you get a more elliptical or oval-shaped orbit. Now, 1 would be a straight line. Now, this next animation kind of is a better representation of what Earth's orbit's like going around the sun. We are not a perfect circle. We're actually closest to the sun in January at 91 million miles, and we're further from the sun in July at 95 million miles. So we actually go faster around the sun in January and slower around the sun in July. Now you can see as the object gets closer to the sun, it is actually moving slightly faster. As it gets further away from the sun, it moves slightly slower. So this is a better representation of planetary orbits. So the next set here shows kind of the orbits of planets and comets. Comets tend to have more eccentric orbits that are closer to, say, 1. Oh, smack. Well, that comet didn't work out too well. Comets tend to have pretty unstable orbits. We actually have seen comets hit the sun, which is kind of crazy. But you can see the planet there has kind of a more circular orbit. Planets have eccentricities that tend to be closer to a 0. Now, when we look at this, we see good examples of Kepler's first, second, and third law. First law talks about how all planets move in an ellipse, and the second law talks about equal area over equal time. And then the third law says, closer you are, the faster you move, and the further you are, the slower you move. So this is a great example of both of those. I really like this animation because it kind of ties in all 3 of Kepler's laws. You know, law 1, all planets orbit in the shape of an ellipse, which you can see here. The second law, equal area over distance and time. We'll talk about that one a little bit later. And then the third law, the closer you are, the faster you move, and the further you are, the slower you move. When you look at the inner planet, the purple one, it's like Mercury. It goes around really fast. If it didn't, it would fall into the sun. Mercury orbits the sun every 88 days. So it's a very quick orbit. Now you move a little bit further out, like the blue one and the green one, and see how they get further from the sun. They move much slower because the gravitational influence of the sun is less. So the planets move slower. So again, this animation is a great example of all 3 of Kepler's laws. Now, we have some really good examples of this in the night sky. Obviously, Kepler, Galileo, Newton, all these astronomers you've heard of, Copernicus, they made observations of the night sky to prove the science that they were studying. So this picture here is a picture of the planet Venus, and you can see it's kind of a half shape. Venus goes through phases, and the reason why Venus goes through phases is because it orbits the sun. Now, when Venus is kind of full and going from full Venus to half Venus, it actually appears smaller. But as Venus is going from half into crescent, Venus will actually appear larger because it is actually getting closer to the Earth. So as Venus goes through these phases, it's going through those phases because it's orbiting the sun. And because of where Earth's positioned and the sun's positioned and Venus is positioned, we can see these phases. We can measure how fast Venus is moving, measuring that planetary motion. And Kepler was able to do that and figure out Venus's orbit and find out it's in the shape of an ellipse and how fast Venus was going. Now this next little sequence is a series of pictures I took of the asteroid Vesta. And you can see its motion over 3 days. I took a picture of it every day for 3 days in a row, and you can see its motion. And this is really how Kepler and a lot of planetary scientists do their work to figure out the orbit of a planet or asteroid or a comet. They discover it, and they don't know its orbit right away, so they have to measure it over a couple of days. And once they can measure its speed over a couple of days, they can figure out the shape of its orbit. Not only the shape of its orbit, but the distance of that object from the Earth and the sun. The next series of images here are some pictures that I took on July 30th to 31st of this past summer. Over several hours, I was able to capture the motion of Jupiter's Galilean satellites. So if we look from right to left, we have Jupiter's moon Ganymede, then Io, and then Europa. Then on the other side of Jupiter, you have its moon Callisto. Now Io actually goes around Jupiter, you can see pretty quick. It actually goes around Jupiter once every 2-ish days. Europa goes around Jupiter once every 4 days. And so you get further out. Again, this was pretty awesome. Galileo was the first to see this and measure these motions of the moons, saying these objects are actually going around Jupiter so other objects can orbit. And over time, we were able to refine those. But these are another way of looking at Kepler's laws of planetary motion, that objects orbit things with larger mass in elliptical orbits. These two images right here are by far probably two of my most favorite images because these are the discovery images of the planet Pluto. Now the picture on the left was taken on January 23rd, 1930. Clyde Tombaugh took these pictures looking for planet X. And then on the right side, you see a picture taken on January 29th, 1930. And you can see the arrow pointing at the planet Pluto and how much it moved in those 6 days. Now, they call Pluto because of the Roman god of the underworld. An 11-year-old girl from Oxford, England, actually named Pluto, which Pluto is the Roman god of the underworld. So there it is. Now, by just measuring that motion, they're able to figure out how far Pluto is. And again, Kepler's third law says the further the object is from the sun, the slower it's going to move. Now, Pluto was discovered in 1930. It was at its closest to the sun in 1989. Pluto hasn't even made one orbit around the sun since we discovered it, because it takes Pluto 248 Earth years to go around the sun one time. So again, this is a great example of Kepler's laws. Pluto goes around the sun in a very elliptical orbit. Matter of fact, it crossed Neptune's orbit from 1979 to 1999. And now it's moving out past Neptune into the Kuiper Belt. So Pluto has a very elliptical orbit, and it moves very slowly. But we're able to figure out Pluto's orbit just by measuring its motion through the sky. What's going on? Just want to talk to you about Newton's law, or not Newton's laws, Kepler's laws. Newton's laws will be next week. But Kepler studied planetary motion. And his first law was that all planets' orbits are in the shape of an ellipse. So an ellipse is an oval. Now, this ball here, see, is not going in an ellipse. It's spinning it in a perfect circle because my hand here is acting as the first foci, or focus, okay? So we're going to talk about what an ellipse is here in a little bit. But Kepler's third law talked about how the closer you are to the sun, the faster your orbit is. And the further you are, the slower it is. So, for example, if I bring this faster, Mercury goes around the sun every 88 days. And you can see how fast it is going. Now, if I start adding more string, you can see how it goes much slower. If I add more, or if I take away the string, whoop, you see how it goes faster. If I add string, it goes slower. Okay, now watch, see if I can do this. See how it gets faster, 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 faster? Okay, like I said, Mercury is 88 days around the sun. Venus is like 240. Earth is 365. Mars is 687. You get all the way out to Pluto, it takes 248 Earth years for Pluto to go around the sun because it's further away, so its orbit is much slower. Less gravitational force between the sun and Pluto is the reason why it doesn't need to go as fast. Now Mercury, on the other hand, because it's so close, okay, Mercury has to go really fast in order for it to maintain its orbit around the sun. Mercury goes around the sun, like I said, every 88 days. It's 36 million miles from the sun, while Pluto's 4 billion miles. So Pluto goes much further. Earth, a little bit closer, 93 million miles away from the sun, goes around the sun every 365 days. What's going on, guys? Mr. Mac here. Just out here to talk about Kepler's laws. We got Jovi on the video. Jovi.
Hey.
All right. We got David and we got Bryce. So we got 3/4 the kid crew out here. We're going to talk about Kepler's first law, all orbits are an ellipse, and Kepler's second law, equal distance, equal time, which is kind of a confusing one, but we're going to talk about it. So, first one is all planets go in an ellipse. So we have Bryce here. Bryce is going to act as the sun. He is my firstborn, okay? He is going to be one foci of the ellipse. So I have a string here, and I have a piece of chalk. Now if I get it taut on there, I draw a circle. So with one foci, I actually get a perfect circle. But none of the planets in the solar system go around the sun in a perfect circle. Jovi, come on over here. Show my, look at that, perfect circle. So, when you have an ellipse that is a perfect circle, its eccentricity is 0. Okay? Now, if your eccentricity is 1, just straight line. Well, how do you get that? David, Bryce, you're going to be one foci. Get over here. Okay? Right here. It's cold. David, you're going to be another foci. Stand right here. Okay? And around one leg. You ready? Ready? So now I have two foci. Whoop. And what happens, thank you guys, with two foci is I now have, David, don't be tripping there. Now I have an ellipse. So when Bryce is at the center, one foci, you get a perfect circle. But when you have 2 points, 2 foci, you end up getting an ellipse. Planets have more circular-like orbits. Comets and asteroids have more elliptical orbits. Earth has a relatively circular orbit. Now, Joey, come on over here. Kepler's second law, equal distance over time. So if this is the sun, what that says is that if you have a planet that's going around the sun, the amount of area it'll cover here is the same amount of area as if it was to cover here. Now the reason why is because the planet is moving much slower here. Much slower because it's further away from the sun. This could be one month of movement. Now you're over here, this could be 1 month of movement, but because it's closer to the sun, it's moving much faster. This is like the Earth in January. We're actually closest to the sun and moving faster. This is like the Earth in July. We're actually further from the sun and moving slower. So this area here is the same as this over the same amount of time. There you go. Kepler's first and second. Bam!